Hello everyone and welcome back. In the previous video we created our tokens and we were about to start the lexers. Let me first explain to you how the tokens work and why do we need them. If you ask what is a token here, it's simple. A token is the smallest meaningful unit of the input expression. Instead of interpreting raw characters like parentheses or plus everywhere, we convert the input string into a sequence of typed tokens with enough metadata for later stages to work mechanically. We will not have any guesswork or no context juggling, and we will have a clean result. We defined 4 token kinds. We have token integer, which is an integer literal. It means it will have an integer like 123 or 0 or 42. We have token operator. This will mean an operator. It can be binary or unary. Binary will mean plus, minus, multiplication, division, and modulus. And unary will have some synthetic unary operators. For example, we will have backquote. It will be for unary plus, like plus 5, or when you have plus 3 in a parenthesis, this will be unary plus. And we will have tilde, like approximate symbol. It will be unary minus, which will be like minus 5 or some number in parentheses. And we have token left parenthesis. This is self-explanatory, just left parenthesis. And we have token right parenthesis. And this will be captured in our token type. So why do we encode unary, plus, and minus as separate operators? The same character minus can mean binary subtraction, like a minus b, or it can be unary negation, which will mean minus a. If we kept them the same character, both the shunting-yard algorithm and evaluator would have infer which one is again later. It will cause some error prone. So in the lexer, we will do, if the start of the expression is, if it's the start of the expression or it is right after the parenthesis, it will see the minus and plus as unary, beginning or parenthesis. If it's like unary plus, it will be the backquote. If it's a unary minus, it will be tilde. In the later stages, we will not be guessing. We will be just looking the operator character. If we see backquote and tilde, we will pop one operand in reverse Polish notation evaluation. If you see plus, minus, asterisk, division, or modulus, these are binary, we will be popping 2 operands. Shunting-yard needs precedence, associativity, to decide when to pop or push operators. We store them directly on each operator token, so the parser becomes table-driven. Here we have our enums, association left, association right. And we have our tokens. This will be for token integer from our other list. The operator will be plus, minus, asterisk, division, modulus, tilde, backquote, and that's all, I guess. We will have precedence, and of course we will have association, but that's okay. So the precedence we will use, for example, if we have 3 and it is unary, we will have backquote and we will have tilde. The second, we will have asterisk, division, and modulus. And then we will have plus and minus. Associativity. Right? This will be for unary operations, so they don't prematurely pop equal precedence operators. And we will have left. This will be for all binary operations, usually arithmetic. Having this on the token means shunting-yard logic is clean, while top of stack operator has higher precedence or equal precedence with the left associativity, we will pop it. This way we don't need a big if-else switch. Tables scattered around, it will be all on the token. How tokens will flow through the pipeline? First, we will have our lexing, which we will be calling a lex function. It will have a input string, which will be converting to t-reg tokens. It will be a dynamic array of the t token here, which will be converting to the digits, which converts digits to a token integer with eval here. It will convert plus, minus, multiplication, division, modulus, and parentheses into the right token types, as operators. It will detect unary, plus, and minus, and it will rewrite them as backquote and tilde with precedence. As we mentioned here, you will have unary, multiplication, division, modulus, then plus and minus. And it will also have some error check. And if there's a problem, we will be giving parse error. Second part, we will be doing shunting-yard. We will have a function called toRPN. We already have the tokens, and we will make them to t-reg RPN. RPN is for reverse Polish notation. It will again uses precedence and association to order operators. It will validate the parentheses, the results in reverse policy notation will be in the sequence of the same T token. It will use the same structs, which means it will have some numbers and operators. And finally, we will have the evaluation. In the function, we will be calling it eval IPN, evaluation of the reverse policy notation. IPN will be our final long result. Token integer will be push to integer. Token operator, if it is backquote or tilde, we will pop 1, apply Unary, and then push, else we will pop 2, B then A, first right then left, then compute A operator B, then push, and we will also be doing division modulo by 0, and it will check the error of divide by 0. Let's talk about why we are using TVEC tokens and TVEC IPN. Basically, we are keeping two dynamic arrays and we initialize them in our main. Tokens will hold the infix and IPN will hold the postfix. This is what the lexer will be producing. This is what the shunting-yard algorithm will be producing. We will be separating them. It will help us debugging and it will keep it kind of simple. Evaluation will be cleaner and linear IPN and no operator precedence logic left. And the TVEC is using a tiny vector, just size, capacity, and element size. So we don't rely on forbidden helpers. We are just keeping everything small and simple. And I want to give you an example. Let's say we have a let's give a concrete example. Let's say we have this minus 4 plus minus 6 in parentheses. We have this equation and we want to lex it. So we will start from the left. And when we first look at the operator here, it is a minus. So we will be saying, okay, this is a Unary minus. Next, we have parentheses, so it is just left parenthesis. Actually, let me say it here. Unary minus. We have left parenthesis. We have another unary minus. We have another left parenthesis. Another left parenthesis. We have our token integer 4. Now we have the right parenthesis. We have the plus sign. And then we have another unary minus. And then we have token int 6. And then we have another right parenthesis. And then we have another right parenthesis. I hope I didn't miss anything. Okay, now we already find the unary minuses beforehand, so it will be easier if it show another example. Let's give another equation here. 1 plus 2 times 3 minus 42 divided by 5. I will just put the lex tokens out. Here we will have 1 plus 2 times 3 1 plus 2 times parenthesis 3 minus 42, another parenthesis, division, and 5. Here we have no Unary, and presence will be stored on each operator token.